Hi ladies and gentlemen, I just want to spend a little bit of time talking about the Einstein summation notation. I found a pretty good reference here, and let me scroll up. This is a work by Ben Yakov and Roig, and this is dating back to 2006, which is just some conversation about the Einstein summation notation. So I just wanted to produce this. As always with my videos, I think that you should probably run this back at 1.25x. I don't talk in a very quick manner oftentimes, and the presentation's not smooth. I don't sit down and do 20 takes to come up with the perfect delivery. So I think you're probably well served to play this back at a little quicker rate. What I want to do is just kind of start over and build some of the basics here that I think are important for you to understand in order to have a real grasp of what's going on with the Einstein summation notation. I'm going to start with the result we understand about the standard basis vectors, E1, E2, and E3, which you're accustomed to seeing as I hat, J hat, and K hat. In general, everybody uses the E subscripts because it's more generic and is easy to extend into higher dimensions. So the first result I want to take a look at here is the result that when we take the dot product between any two of these vectors, and remember we have really only one rule for Einstein's summation notation, which is when we have a repeated index, that means we're going to sum through that index. And as we've done for the rest of the course, we're going to assume that all the indices run from 1 to 3. So in this case, we just have one standard basis vector dotted with another standard basis vector. And from the definition of dot product, what we realize is the only way that this is non-zero, so this is equal to 1 whenever I is equal to j, and it's 0 otherwise. Right? So this thing's equal to 0 otherwise. So I'm not using strict mathematical notation here. I'm just trying to provide you with some insight into what's going on. So what the paper says is, hey, look, this dot product is equal to what we're going to call delta ij. We did not spend a lot of time talking about delta, but it's integral to everything that's done with Einstein's notation. So I think it's worthwhile for you to make sure that you understand this. So what I'm going to do is highlight the things that if I were you, I would definitely know. And one of them is, of course, this, which you can argue is obvious, and I'm not going to disagree with that, but I would certainly know that. Another one is this, understanding that the Kronecker delta is equal to 0 when the indices are not repeated and is equal to 1 when they are repeated. And as we discussed before, and the same is true with this paper, which is one of the things that makes this paper nice, the indices are running from 1 to 3. So I would definitely do that. One thing to note here, however, is notice that we have something with two different subscripts, I and j. This is going to take me to my third point, which is making sure we understand what these things actually represent. So in the case of a sub I, what that means is I'm going to let I sequence 1, 2, 3, and that is going to give me a vector. This is equal to A1, A2, A3. I have three distinct components, and that's what that notation tells me, is that I have those distinct components that are just components of a vector. So then similarly, what is ijk? Well, in this case, and let me shorten this up a little bit, right? This is going to be A11, A21, A31, but now I have to cycle through j, and since the indices are not repeated, these are separate elements. So this is A12, A22, A23, and A13, A23, A33. So this notation, and you begin to see some of the efficiency of the Einstein notation, this thing represents a matrix. So this represents a vector. The A sub ij represents a matrix. Then that begs the question, what is A sub ijk? And the answer is, this would be something that looked like the matrix here, except every k index would be 1. So it would be the same thing, but it would be A11, A121, A131, etc., A331, and A221, and all the rest of these items here would be the same. And then I'd have another one of those. So I'm actually expanding in the third dimension here. I'd have another one where I'd have an A112, etc., over to A312. And so this is the third order tensor. That's what it represents. So this is the third degree or third order tensor. And now you can really begin to see the efficiency of being able to write it simply as this. So I just want to provide that background to what the Einstein summation notation is about. It's shorthand with really only one rule, which is repeated indices mean that we are going to sum things together. And in our case, from 1 to 3. Forget about these over here. These are examples which I'm going to run through once we finish. But right now, I just want to continue walking through my numbered list here to make sure I don't forget anything. This, let me just say, this piece here is the same as what we've been writing. This is a vector, which is A1 I hat plus A2 j hat plus A3 k hat. That's how you're used to seeing that. That's familiar to you. And then, of course, just as they're representing here, we really are using the E's now for the standard basis vectors. And A's, we don't use capital A's, we use capital letters for matrices, lowercase letters for vectors. So it's a little bit different. I just wanted to clarify that. And so we see that very clearly right here. And this was not something that we emphasized, but actually turns out to be important when we're trying to use Einstein's summation notation. That vector is represented this way. So you see that we have a repeated index, which is the subscript I. And so I have the components, AI, each component being multiplied by its respective standard basis vector. So literally this is A1 times 100, and then A2 times 010, and finally A3 times plus A3 times 001. So remember, the repeated index is the summation, of course. Moving down then, taking a look, this is the example that we did of dot product, and this is a result. So this thing here really is box. I would definitely know this because this representation for A is one that is used consistently in order to do some of the identities and some of the proofs. So down here is the dot product. They do a really nice job of kind of walking through this dot product and what they say. And this here is the better argument. This is the piece I want to focus on down here. This is the piece I think is more important. And so I'm not going to repeat this, but what they're saying is, hey, each vector is represented as its components multiplied by the standard basis vectors. And so I have an AI, EI dotted with a BJ, EJ. The AI and BJ are scalars, so I just pull those out in front. The E's are both vectors. They're both standard basis vectors. So the dot product really, and if I were to put a parenthesis in here, the dot product only applies to these two vectors. But from what we've learned previously, this dot product between standard basis vectors is the delta function, ij. And that is equal to 1 or 0. When it's equal to 0, I don't care what it is because obviously it's not contributing to anything. So when it's equal to 1, that's when I equals j. So this really becomes kind of IJB, AIBI. Apologize for that. And then a delta II, which seems like it might violate our rule for only being able to repeat a subscript twice. But the fact is, we know what this is. For all the possible I values, that's just 1. And so the result simply becomes AIBI. So I guess my point to you is, sure, you want to have this in your bag of understanding, and you definitely want to know that that is a true statement. But I think it's illuminating to understand the argument of how that comes about. And we'll see that a little bit more as we move forward. So let's take a look at number 6. This is just another representation. Again, the vector is represented as its components multiplied times the standard basis vectors, and then the index is repeated to show the summation. I wouldn't worry about this. These things are not things that we discussed at all, and I don't think any of this is, I mean, you could figure it out. I'm not suggesting you couldn't. I'm not sure that that's relevant to what we're doing. So the next thing is really the permutation tensor. And I talked about this, so I'll just briefly remind you in kind of a shorthand. I have my clock, right? And anything that goes this way around the clock gets a +1, and anything that goes this way around the clock gets a -1. And then if I have a repeated index, it's equal to 0. All stuff that you've seen. That leads to this result here, which is really important, and I would definitely memorize this one here. Understanding that when I take the cross product of standard basis vectors, we're going to end up with the permutation tensor with I and j. Notice I'm matching with the I and j here, and then the k matches with my k component here. And examples, we did several examples like this. We did several examples like this when we did the homework problems. But you know, you could have an E3 and you could cross that with an E1, and what you want to make sure you understand is that that's epsilon 3, 1, and then call it K or J or M. Remember the indices, it doesn't matter, E, J, right? So it's equal to this. And then how do we evaluate this? Well, since the permutation tensor can't have repeated indices, the j can't be 1 and it can't be 3, because when it's 1, epsilon is 0, and when it's 3, epsilon is 0. So this just really leaves me with epsilon 3, 1, 2, e hat 2, and now I look at this and see it goes clockwise, 1, 2, 3, and so this is equal to e hat 2. We did examples like this. I think this is a useful tool, and I would certainly know that one. Moving on then, I don't think, I mean, this is true. This is kind of a gee whiz fact. I don't think it gets used very often. I wouldn't worry about it. And that brings us down to the cross product and understanding the cross product. And same as it is with the dot product, I think that this argument is important. Certainly you want to know the result. Certainly you want to understand this result. But I think this argument is important. So same as we did before, they've replaced the A vector and the B vectors with this form where they have the components multiplied by the standard basis vectors. And there's the cross product there. And the reason that this is relevant is I have the A, I, and BJ are constants. Those come out in front, and what I'm left with is really the application of the cross product just to the basis vectors. And that gives me this EI crossed with EJ. Well, from the previous result, we realized that the EI crossed with EJ is simply this permutation tensor times EK. That, now that I have the AI and the BJ, which are just scalars, so I can bring those to the inside, gives me this result. Again, I think this result is important, and you'll see why. There's a bit of a summary at the end of this, which is somewhat clever, I think, and intuitive. And so I would certainly know that result for cross products. So I'd know the basic dot product, the basic cross product, that kind of information. Coming down here, now we get to what I'm going to call epsilon math. We did not do any of this. When we did our work, we did not look at what this thing is as a tensor of Kronecker deltas. We didn't do any of that. I wouldn't worry about that. All I'm going to tell you, same thing here, right? This is, if you want to learn more about it, I would certainly work through these derivations. I don't think you really need that. I will tell you that even though we didn't cover this, it is one of the more important facts that is used when we look at using Einstein summation notation. So that's just for your personal benefit. And this recap is the part that's interesting. So what the recap says, and I apologize, it's a little bit sloppy here with my pen. What the recap says is these facts. So the facts basically that I said that I think you should memorize. So the dot product of the standard basis vectors is the Kronecker delta. The dot product of two regular vectors gives me this repeated index here. The cross product of the standard basis vectors is the permutation tensor, and then the last component the last index is equal to is the same as the standard basis vector. The K matches up here. That's what I'm trying to say. And then of course the cross product for two vectors is equal to this thing here. And it says that these relationships along with equation 20, and that's this is what I call epsilon math. This is the simplification when you have a product of permutation tensors. So over here's a product of permutation tensors, and that can be rewritten as this series of Kronecker deltas. Again, we didn't do any of this, but just FYI, that is an important piece. But between that and these relationships, you can more or less prove all of the vector identities. And so they give some examples here. Here's a proof of vector identity, which I'm not going to go through because this exceeds what we did in this class. You see here is the epsilon times epsilon, which is where that equation number 20 comes in. We didn't do anything like this, and that being said, you know, if you want to know a little bit more about it, I think that there's interesting. One thing we did do, which is my last numbered item here, is number 10. We did take a look at this dot product and cross product combination, and you see the way they handled it. They replaced the A with its representation as the components times the standard basis vectors. They left in the dot product, and then they wrote out this simplification for the cross product. And then what they do is with the dot product, the only vectors in this entire expression here, this one, the only vectors are E sub I and E sub M, and they bring those in. And then they make the replacement. And they say, hey, I know E sub I dotted with E sub M is the delta. Moreover, what I know from this, and this is not in here, so I really want to highlight this, is I am now only interested in situations where I equals M. If I is not equal to M, this whole thing gives me a 0. And so what I can do then is I can replace all the M's with I's, and you can see that's what they did here. So we end up with an epsilon, JK, replace M with an I, and then we have an AI and a BJ and a CK, and then a delta II, which again, we're only writing in temporarily because we know that this is equal to 1 for any value of I, and we're left with this result here, which is exactly the result that they give us down here. Now, they did swap around the indices, which we can do, but because it's a permutation tensor, every time we do a swap of these things, we are actually changing sign. So you see what they did was they did one swap to make this EJIK, which would actually require a negative sign out in front, and then the AIBJCK. And then they did another swap, which is epsilon, and they swapped the I and the J, which makes it IJK, and then it's AIBJCK. When they do the second swap, another negative sign, which brings us back to being positive, and that's how they come up with their result. So when you look at this, if you try to dissect this, you'll see those swaps are in there. All right, I'm going to pause it right there. All right, if you want to continue with me, that's fine. Otherwise, just shut this off. What I'm going to do is walk through some of the examples that we had in the pre-class material, just to try to emphasize some of these points. I've already shown you kind of how to dissect the important parts, what I consider to be the important parts of this little paper, and the things that I would memorize if I were you. And it doesn't hurt to do some more memorization or at least understanding of some of these other facts. So let's start with this gradient, and I've switched over to blue, so I'll be writing in blue here. So the gradient, right, is going to be a series of partial derivatives. So I'm taking the partial with respect to I, and what this really means, let me be clear with this. So I'm taking the partial with respect to x sub I, which is being shorthanded as the partial with respect to I, where the functions, f is a function of x1, x2, x3, and so I'm taking the partials with respect to x sub I, but we're writing it in this shorthand notation, just to make sure we're clear on that. So this is the partials, and they're applied to f. And that's it, and this gives us exactly what we would think, right? This is the partial with respect to x1 of f, and then partial with respect to x2 of f, and partial with respect to x3 of f. And no surprise, because we have only a single index, that's going to be a vector, and we get a vector out. Whether it's a row vector or a column vector, it doesn't make any difference, those two things. In this case, it doesn't matter because we're just talking about the fact that it's a vector. So now what we have is a situation where we have the gradient, which is, again, the del operator, which are the partials with respect to x1, x2, x3 respectively, applied to a function that is a vector function that has multiple components. So I'm going to write it this way. And we can see, because I have two indices that are not repeated, this is a matrix. And I'll let you go back and look at the homework that you had. I think it was lesson 2 where you actually looked at what this was. So the divergence. The divergence is now this thing, which I'm going to write as this partial with respect to I, E, I. Right? That's really what it is. When we think about the gradient, that's what we're doing. We're applying this partial derivative, but we're applying it at each component. So similar to the way that they kind of write their vectors in this notation, A, I, E, I, we're going to do the same thing here. And the reason is because I'm now going to take this and I'm going to dot it with the F vector, which is just a series of F elements, Fj, E hat J. And what I get out of this, similar to the argument that they have over here with the dot product, is I have this partial I Fj times Ei dotted with Ej. This thing is equal to 1 when I equals j and is 0 otherwise. So what that gives me the fact that these two are going to have to be the same. So it's the same type of argument. So that's the divergence. It's this dot product, and it looks like this. Similarly, the cross product, it's going to be an epsilon ijk, where I have the partial with respect to x sub I applied to each f sub j in the direction of ek hat. The definition, if you will, of the curl, which in this case, or the cross product rather, which in this case is the curl of the vector field. This one here again was a homework problem. This is the del operator dotted with the del operator applied to f. And so this thing again is that partial I, E, I, that's the del operator. And then we already know what this gradient is. So that's dotted with this partial I, F, I, or sorry, Fj, it's my bad. Fj, sorry. Right, so it's that partial I, Fj, and it's dotted together. So this thing, right, is, yep, that's the gradient there. And okay, well, and this is the way it goes. It's a little bit of back and forth. This is kind of what I've learned here. So we have this dot product, but this representation is for a matrix. And so I'm applying the matrix, but I have this dot product, but I don't have, right, anything else. So I'm going to remove this out of here, right? And then what I really am ending up with in this situation is I'm ending up with this applied twice to all of these entries. All right, let me scroll up a little bit here and we'll do a couple of examples. So again, we have this dot product. So I'm going to represent this, at least initially, as partial I, E, I hat. That's the representation for the del operator. Then the curl of f, which I see I have up here, so I'm dotting that with epsilon. I've already used I, so I have to move to the next index, j, k, l, and that's partial j of f of k and e hat l. Everything in here is a constant except the vectors EI and EL, and that's where the dot product applies. So I have an epsilon j, k, l, and I have a partial I, and I have a partial j, and I have an fk, and then I have a dot product between EI and EL. And what this means is that L has to be equal to I. So L has to be equal to I, because that's when this is going to be 1, otherwise it's 0. So I'm going to come back in and replace the L with an I. That's an epsilon j, k, I, and then a partial I, partial j, and an f, k. Now at this point, I could rearrange, again using the swaps, I could rearrange this, and I could say I could swap k and I, and then I could swap the j with the I, and I'd have an ijk, and because I did 2 swaps, then I would still have an even permutation, which means I don't have to put the negative sign out in front. It's already taken care of. But what I think is really more interesting to do the proof here is just to break this up into its parts and take a look at it. So you remember from the conversation about the permutation tensor, I only have 6 non-zero things to consider. So I'm going to write them out in this fashion. I have a 1, 2, 3, and a 1, 3, 2, and a 2, 1, 3, and then a 2, 3, 1, and then a 3, 1, 2, and a 3, 2, 1. So I'm going to go through each of these. So notice right there, it's I or JKI. That's the designation here. So it matches with the epsilon. So these are the J's, and these are the K's, and these are the I's here. And so I'm just going to write this out. What is this going to give me? Well, it's going to give me a J of 1 and an I of 3. So I have a partial 3, partial 1 of F2. And then here I have a partial 2, partial 1, F3. Notice the 1, 2, 3 is clockwise, so that's a positive. This is 1, 3, 2. This is running counterclockwise, so this is actually a negative here. Then I have a 2, 1, 3, and that's going to be partial 3 and a partial 2, F1. And again, I'm running 1, 3, 2, which is counterclockwise, so that's a negative. And then over here, this gives me a partial with respect to 1 and a partial with respect to 2, and then an F3. And that's running 1, 2, 3, so that's clockwise, that's positive. And then I have a 1, 2, 3 here, so that's a partial 2, partial 3, F1. And then finally, I'm running counterclockwise, which is going to give me a negative, and that's a partial 1. I is equal to 1, J is equal to 3, so that's a partial 3, F2. And then here's what I want you to recognize is the fact that as long as F is sufficiently smooth, which was part of our assumptions for these problems, then I have a partial 3, partial 1, F2, and a negative partial 1, partial 3, F2. Those things are equal, but opposite signs, so they cancel out. And then here's a partial 2, partial 1, F3, and here's a partial 1, partial 2, F3. Those are equal and opposite signs, so they add to 0. Similarly, these add to 0, and the result is this whole thing is equal to 0. That was one of the homework problems. This is the primary use for Einstein summation notation, is to prove these vector identities. So I want to do just one more, and then we've been on for far too long here. Let me do one more. I'm going to skip this one. This one includes, sorry about that. This one includes epsilon math, and since we haven't done any epsilon math, I'm not even going to show you that it includes epsilon math. Just take my word for it, it does. So looking at this one here, we have again the partial IEI. That's one way to write that del operator, crossed with, and now I have a gradient, which is partial JF. All right, so looking at this then, I have the cross product, which I know is going to be an epsilon I, j, k of the first thing here, which is partial I, e, I hat, and then the second thing, which is this partial j, f, and then I have an e, k. So again, another example where I say, well, I didn't really need to use this piece here. That's not helping me. Because remember, the del operator could be written as either this or this. They're equal. They're equivalent. This is part of what makes Einstein notation difficult until you get used to it, is the fact that, hey, wait, these are different, or the same thing rather. And so what we're going to do is we're just going to drop this off. So I'm not going to include this. And now I have this set up here, and looking again at my combinations, I go through the 1, 2, 3 and the 1, 3, 2 and the 2, 1, 3, and then similarly I have a 2, 3, 1 and a 3, 1, 2 and a 3, 2, 1. I'm not going to go through all of these, but what you'll see, of course, is ij, so I have partial 1, partial 2, f in the e direction, e3 direction. Okay. And then this is a partial 1, partial 3, f in the E2 direction. Remember, it gets a negative because this is reverse order. And then I have a partial 2, partial 1 of F in the E3 direction. And this one's also negative. And what I want to highlight here, I'll do it in green. What I want to highlight here is this one and this one. Just as we saw previously, as long as F is sufficiently smooth, these partial derivatives are equal and these things cancel out. And so it's going to give me 0. And it turns out that you'll get pairwise cancellation just like we did here. And this entire thing is actually equal to 0. Again, primary use for Einstein summation notation is to do these kinds of proofs. And that's it. I hope this is helpful. And if I ran on too long, I apologize for that. Thanks.